Okay, so this is a mathematical derivation, so they are always equal all the time. All right, so it basically, in short, that's the difference in terms of the formula, and I've already explained why uh, we have to deal with both population and sample definitions of variance and also the standard deviation. So now, and then we want to just quickly take a look at another term, which is essentially uh, something we have already known about, right? So this term here, we call it variation, for lack of a better term. It's not really uh, a standard definition, but I think widely used enough. So a variation, what is variation? It is symbolically represented as SSXX, yeah, and it is SSXX because well, this is a square here, so we are having one copy of xi minus x bar times another copy of xi minus x bar. This SSXX will revisit it somewhere further down in the lecture series, where we might see SSYY and then SSXY coming out right later on. But for now, let's recognize this summation of 1 to n xi minus x bar square, and that is actually this particular term here, yeah? Can you recognize them as the same? All right. So in other words, it's like, well, simply said, this is also equal to, if we just divide by n minus 1, we should get back sample variance. And that's exactly correct. All right. So we're just giving this summation a special recognition, right? So we call it variation, and we crown it with a symbol that is its own, and it's called SSXX. And that's very useful because the next time we want to talk about, hey, you know what? Let's sum up all the squared differences from the mean, which is a very useful notion. Uh, then how should we call it, right? So it's a mouthful. We just say, let's calculate SSXX. Yeah, so that's the idea. Now, let me just kind of quickly give another pictorial idea, right? So the idea is that if we have a x-axis, remember x is a measurement, right, of height of students, weight of students, student score, quiz scores, or employees' income, customers' budget, and so it can be all kinds of measurements. And let's, for simplicity, say that let us look at well, both are the same, right? So I'm just going to use x bar first. So let's suppose x bar is 10. Okay, so this is our x bar after calculating and finding the mean. And then we have some xi's here. So the xi's can be, for example, 9. One of the data item is 9. All right. So xi minus x bar is -1, -1. And if we square it, that's 1. But what I want you to understand is that, so one data item is here, and that's the mean, it's 10 here, right? Let me change color a little bit. So the xi minus x bar will actually be this line here. And the squaring is interesting. The squaring is going to create a square, right? So we're going to draw as tall as it is wide, and the area here will be this square of this bracket. Yeah, and we haven't done the summation, but let's create a few more blocks. So if you allow me, then suppose another piece of data is, instead of 11, we call it 10.5. All right. So 10.5 and minus 10, we have a 0.5, and then we need to create a block out of it, and that's our another contribution of the area. And we can continue to add more and more areas, right? But I'm going to mess up the screen more and more. So if we have an 8 somewhere here, then it's going to create a 2 by 2 block, all right? And that area is not going to exclude the blue one. It will also include the blue one, right? Overlapping it. Yeah. So there will be a double count, and yes, that's also the case. All right, and so on. So we keep adding more and more, and there can be a 11 here and a 12 here, So let's just have a, it can be 11.2 even, right? So we just raise it, right? 1.2 units tall, and then we add another square here. You follow, right? So we have all the squares all aligned with one side exactly on 10 itself. Why is it 10? Because 10 is our x bar. So if you have all these squares done up, then basically you have all the x1 minus x bar squared, x2 minus x bar squared, x3 minus x bar squared, and so on. So you have all the squares visibly shown there already and aligned at 10. Then what you do is you add up all the squares. That's the summation. All right. And if you divide by n minus 1, if you divide by n minus 1, or capital N in the first place, in the first formula here, then what we are trying to do is to find the so-called representative square. I'm kind of showing it on the left side of the 10. All right. A representative square, which is the average of all the squared areas. All right. For sample, of course, it's slightly larger than the square areas because we're dividing by n minus 1. But the qualitative view is the same. We're trying to find an average sized square. Remember, the side and the height are the same. A square that is indicative, that's average of all the big and small squares that have been induced, created by xi minus x bar square. Yeah, so in the case of xi minus mu square, it's the same. So instead of calling 10 x bar, it would be that the population mean ended up becoming 10, and then all the squares will be aligned at 10. All right, so I mean, it doesn't have to be 10, just any value that mu represents. Okay, so another point, sort of a secret technique I use is how to remember all the notions of symbols. How do I remember all these? Now, there's only one simple rule. All the Greek alphabets denote the measures, parameters, attributes, values related to population. All the alphabets, like S and SSXX, all these, right, non-Greek letters, they refer to the sample measures. So if you see sigma square, you don't have to ask, does it refer to population variance or sample variance? It has to be population variance because it is a Greek letter, right? So if you see mu, maybe you forgot what mu means, all right? Is it average or standard deviation or what? I can't remember. But you do know it is about the population. Why? Because mu is population. Mu is a Greek letter. And of course, we do know that mu represents population mean. So please do not carelessly use the symbols, right? So for example, I have seen students writing, let the population mean be x bar. And that is a problematic sentence because you want to talk about population mean, and everyone in the world talking about statistics will refer that to mu. All right, and mu is, although a Greek letter, it is also the chosen Greek letter. So don't try to use alpha. It's a Greek letter, but it is and say let alpha be the population mean, and that's quite a awkward sentence as far as statistics is concerned. So we don't try to write that. Okay, so and therefore SSXX, you remember it as the sum of all the squared deviations, but you forgot whether it is to minus x bar or it is to minus mu for a moment. But hey, SSXX, right? Has it got any Greek letters? Nope. So it has to refer to everything about the sample, nothing to do with the population, right? So in that case, then we cannot have a formula that is referring to the population something. And therefore, it cannot be mu. And so it has to be x bar here. All right, so it's kind of like a little bit of a side understanding that will help us, I won't say memorize, but write down the formula confidently and kind of double checking it. Because when I write summation xi minus where's my cursor? Where's my cursor? Okay. When I write summation of xi minus mu square, all right, and call it SSXX, something weird is tinkling, right? So I wouldn't quite be very settled with it, and I wonder what's wrong. Oh, because SSXX is talking about sample, so I shouldn't be having a mu here, right? So therefore, I will correct it as X bar. Yeah. So all these will be to help you internalize the definitions and the formulas and the symbols and the notations much more easily because it's more organized, and actually there's a secret standard to it, right? So the Greek letters talking about population, the non-Greek letters, the alphabet, refer to samples. Here I just want to quickly run a little bit of a Excel to concretize a lot of these calculations that we talk about, right? So let's roll up our hands and sleeves and uh, try to work out a bit of calculations here. Now we have some numbers, right? So I'm going to just enter these numbers. So remember, I was asking you to think about each random variable as if it is like one column in Excel, and indeed that is quite the case here. All right. So I would just quickly enter these numbers. I didn't pre-type them because I want to show you it is really from scratch. I have nothing secretly prepared or some formulas hidden that I am not showing you. Right. So how many numbers are there? Altogether 9 numbers. Yep. Okay. So the illustration here is divided by 9, and we have a total count of 9, and the symbol is sigma square. So we're treating x as if it is a population. Okay, so first thing first is we want to calculate the mean. Now, so let me insert so that I can say the mean is mu. All right, that's the population mean. Population mean in Excel is very simple. Just do the averaging. All right, and then we are done. So that's 99, and you can see why we have all these 100 minus 99, 102 minus 99, and so on.